Second paper in this session is procedural sound generation for soft bodies in video games by Feng and Joslin from Carleton University. And the paper will be presented by Feng.
Alright, so I have to apologize for the technical issues a little more because I was working last night and for some reason the sound doesn't really play, so it has to come from my straight from my computer speakers. But anyways, so hello and good morning. So my name is Feng. I'm a PhD student from Carleton University in Ottawa, Canada. So I'll be presenting a paper titled Procedural Sound Generation for Soft Bodies in Video Games. So recent advances in games have made it possible to generate high-quality graphics and physics simulation for soft bodies. So this ever-increasing amount of realism has posed many unique challenges to create the corresponding audio. So soft body sounds are usually quite noisy, yet have a very natural and organic characteristics. Moreover, due to their complex structures, simply using traditional pre-recording audio will not be enough to precisely capture soft body's deformation and contact states. So we also need to consider the CPU and memory budget, as soft body dynamics themselves would consume a large amount of computing power. So in this paper, we propose to use procedural sound to synthesize soft body audio in video games. Our method is based on data-driven approach, where we develop a simplified parametric estimation model to calculate soft body motions and use a fast feature correspondence to index pre-recorded audio clips according to these motion signals. We also derive an automatic CSS-based technique with user-specified parameters for more control, which can generate possible soft body sounds such as calls and roping in real time. So the importance of procedural audio generation has been recognized for a long time in the computer graphics community. One particularly interesting topic is the synthesis of rigid body sounds. As most of the rigid body materials are homogeneous, they will exhibit strong ringing tones under an external impulse, thus their sounds can be modeled using physics-based approach such as linear model synthesis, finite element method, and pre-computed acoustic transfer, which is to estimate the acoustic pressure and the of model vibrations. To accelerate the computational speed of the model synthesis, several optimization methods have been proposed, such as less-range systems and the frequency-domain model synthesis. To address more complex sound phenomena, a number of works has been focusing on resolving contact-related deficiencies, although physics-based methods are able to achieve accurate and high-quality results if they are usually very slow and require a lot of parameter tuning, which makes them quite impractical for real-time applications. Therefore, some other researchers use a different approach called data-driven synthesis, which reproduce sound based on the characteristics of recorded data. So beyond rigid bodies, there are also a number of works focusing on simulating the sound of rigid bodies, such as the essentials, bubble-based fluids, as well as soft body sounds, paper, pulse, and slinking. Since most of these objects tend to undergo large deformations, which cannot be practically simulated with physics-based methods, it would be easier to use data-driven methods that analyze and reproduce sounds based on pre-recorded data. So our work is inspired by previous data-driven approach, in particular the work of Carleton. However, the focuses are different. So Carleton proposed a two-step synthesis, where they first generate a low-quality target signal, then use CSS to piece together class recordings to best match the signal. So such mapping process also involves a number of listen-manual correspondence, which results in slow simulation. In comparison, our work is more generalized and can be applied for both pulse and rope. We also introduce a fast feature correspondence based on speed accuracy trade-offs and a number of simplified sound models to bring down the computation time. So here's an overview of our method. We first pre-record a set of sound database containing relevant short audio segments. Then during gameplay, we take any soft body object and feed it into our parametric sound models to detect sound producing events. Next, based on these motion signals, we use CSS to select and synthesize microsound samples from the corresponding database. Finally, depending on the player's location, we add some specialization effects to enhance the immersion. Alright, so let's take a look at this parametric sound models in more detail. So to generate familiar soft body sounds, we choose class and rope as our primary objects. So our class sound models are similar to Anatol, where given an input class object, we divide the produced sound into friction sounds and prompting sounds. So for friction sounds, we use the average sliding speed to approximate the changing pitch and the sizing of the contact gradient to determine the volume of the sounds. So as a result, we obtain a friction sound model F at each frame T, which is sufficient to model this sliding contact events. Next, to model the prompting sound, we estimate the bulking event of the pulse by analyzing its mean curvature H, as well as its energy change using this equation. We then measure the total of this energy to indicate the amplitude of the final audio, and as a result, we produce a list of bulking events C with the total energy E. So now let's take a look at the rope sound model. So for any given rope object, we identify three types of sounds. A sliding sound we call external friction sounds, a scratching sound called internal friction sounds, and a whoosh sound or aerodynamic sound. So similar to class friction model, we use the average sliding speed and the contact gradient size to output an external friction model F to drive the synthesis of the sliding sounds. For internal frictions, we measure the average change rate delta S of the rope lengths to model this kind of sounds. Finally, when the rope cuts through the air with a fast speed, it will create sudden fluctuations of pressure that produce sound which is called Aeolian tone. As a result, we can use the predicted Aeolian frequency F of each particle P on the rope to approximate the generated aerodynamic sounds. So to synthesize the final audio using our parametric sound models, we construct a database of pre-recorded class and rope sounds. So for class sounds, we create two separate databases using 5 types of common materials, which are corduroy, silk, linen, polyester, and cotton. As you can see here, to record friction sounds, we basically fix a large piece of cloth on the wall and use smaller cloth patches of different sizes to slide against it at various constant speeds. We then order these clips in a contact gradient size versus speed matrix. Next, to isolate the prompting sounds, we simply just mount the cloths of different sizes onto metal bars so that we don't get sliding sounds. We then just shear the cloths up and down at many constant frequencies, and this effectively gives us the variety of prompting sounds in a matrix of cloth size versus energy. So similarly, we record a rope friction sounds with two materials, sisal and polypropylene. So for aerodynamic sound, our goal here is to get a database matrix of rope length versus speed. And to do so, we simply spin the rope in a circle by holding different spots on it and just slowly increase the speed until it makes loud whoosh noise, as shown in this one. So now that we have both the sound models and the database, we can begin to synthesize the final audio. So our method is adapted from CSS, where we segment our source database recording into units and use a unit selection algorithm to try and concatenate these units so that they best match the target sound models. So let's take a look at this data type segmentation process. So as our database are made of continuous friction noises and discrete impulses, such as prompting and Aeolian sound, we need to treat them differently. So for continuous sound, we basically extract a number of short clips, convolve them with a triangular window, and put them back as sound matrices with a label such as size and speed for each clip. And for impulsive sound, we simply extract each discrete impulse event, convolve them with a rectangular window, and then label and store them back as sound matrices. So the next step is to select these units for our target sound models, as we can see from this table. So given any output sound model, we need to find the corresponding database units according to the labels. To do so, we take the approach described as follows. So for speed, energy, related datasets such as these. We can approximate the correspondence between source and target using linear interpolations and some nearest neighbor criteria. However, we also have other data where the source and target distributions are very different, such as these size-less related datasets. Therefore, we introduce a user-defined correspondence to manually walk the source units in the space of the target using a non-one mapping. So now we came to the actual synthesis part. So for friction sounds, we constantly monitor the output of our friction model F at each frame. So given any parameter L and we use the algorithm described earlier to select the corresponding database unit with the label as we. We then skip over for a few frames and begin to synthesize the next one. So the final output audio is a segment sequence of many short units with 50% overlap, and it also avoids repetition and large jumps between units. So for prompting sounds, we look at the bulking event C at each frame. We then calculate the total MGE and find the matching datasets unit with the label SE. So next we look for another unit from the database after a few frames, and finally we concatenate them together to form the final audio. So similarly, we also synthesize the rope sound and PC for more detail. So last but not least, to further increase the realism of the results, we add some spatialization effect. So after synthesis, the sound will be played at the location where the motion occurs. So to attenuate the sound in regards to the player's actual position, we set up two border radius, R main and R max. So that when the player is inside R main, the audio amplitude will be at the max, and when the player is in between, it will fall off naturally. Finally, we also implement a signal HRTS system at the camera for real-time binary effect. And here are the results. So we use unregulated Ford with a soft body simulator plugin called Microdynamics, which is a particle-based system running on the CPU. All sounds are synthesized at the 16 bits, 44.1 kHz, and the frame rate is typically about 60 FPS, with a relatively low CPU load and fast synthesis time. So I will show some clips, and ideally it will need to be heard with microphones. So please do see the video when you get a chance. So you get the idea. We also did some comparisons between our synthesized results and the real-world recordings, and here's the clip. So we can see that overall our results exhibit similar characteristics compared to the real ones, with some minor variations due to the different nutrients involved. So as for in conclusion, we have presented a real-time system for synthesizing plausible solid-body sounds in video games. For practicality, we developed a number of simplified parametric sound models, as well as a fast DSS-based synthesis method, which is valid for minor solid-body interactions and ideally can be extended to other particle-based systems. It also consumes less memory and is more efficient other than other derivative methods. So as for limitations, currently our system does not work with Carleton closing and higher physics. It's not accurate enough for more complex interactions. We also need to expand our database to include more sounds, as well as develop a simpler and more intuitive interface for specifying parameters. Lastly, we didn't really address the issue of sound propagation, and in the future we will consider a better HRTF and potentially integrating our system with VR and haptics. And that concludes my talk. Thank you very much.
Thank you very much. Other questions? Yes.
Hi. I was just wondering, since you mentioned using it in games, how many audio clips do you need to define a subcloth in terms of the different parameters, and how much time does it take to actually do the evaluation on the sound synthesis?
It really depends on what kind of database you want to build. So for R, we just simply divided the sort of the sound into two categories: one for the friction and one for the clumping. And for frequency, the synthesis time or the evaluation time is typically under well, regardless of the the manual correspondence time is typically under 1 minute. And it's doing offline, and it only anytime we done once, and it can be reused for multiple times. So, and the synthesis time is typically under, I would say, yes, typically under 6.35 milliseconds.
So for the examples you showed, how many audio clips would go into those?
Pardon me?
For the examples you showed there, how many audio clips would you need to build that level?
Audio clips. I would say typically between 15 to 20 audio clips. So yeah.
Cool.
Any other questions? So I had one. Actually, it was I really liked the interaction of the character, which you had at the beginning. But I noticed that, if I noticed correctly, even though you were synthesizing different materials, cotton, silk, the animation was the same one. So did you think about also have the physics animation, like the person going through the curtain, but model the curtain also physically with a different material? Because I think somebody going through a curtain is going to be different if the curtain is cotton or silk. The sound was different, but for me it had a little bit of an uncanny effect because I saw the same video. It was a different sound, but the same animation. So did you think about also modeling, to have examples where we model the physics of whatever material it is?
Yes, so we definitely consider different material. It's just not so obvious in the video shows in here because the sort of the bottleneck of the software simulator we use, where it doesn't really consider different materials. So what we can do is that we just manually adjust the tension and sort of the force between each particles to sort of the silk is more lighter, so that it should react more towards the force, and for higher materials, so that polaroid it should be heavier, and such that when the balloon is blowing the clouds, you can see that for color rate sort of fluctuates slower, as for silk, it sort of flies like a flying rice. So yeah, it's definitely should be considered.
Anybody else in the audience? Otherwise, I'm going to still show another question. Yes.
Thank you. You said that you cannot simulate clothing.
Yeah.
Why can you, I mean, if you use the same material as you presented, why can't you simulate clothes if you only wear?
Well, that's because the soft body simulator doesn't really have a target clothing, and for Unreal Engine, it has this dedicated clothing physics, but it doesn't really like it's not really compatible with the system or the algorithm we use. And the main issue is that it doesn't really give us access to the particles or the information of the particles. Definitely, it is something we will consider in the future.
Okay.
But technically, it will work with it. Because all we need is the sort of the positions of the position of each particle on the clothes, so that's it. And technically, we should compatible with it.
Was there another question there? Let's take one more question. Can you speak loud? Because I think
It was just in the back-to-back comparisons you had with the real-world cloth examples. So thank you. You in the real-world video, you would get like sort of a nice, smooth friction sound as the ball was dragged across. In the virtual example, it was a lot more stuttery, I guess. The sound would sort of come in and come out, and I was just wondering if that was an artifact of this synthesis system or if it was more the underlying physics system.
It's more of the underlying physics system because it depends on how many particles you want to select for the class. And for this one, we use a 30 by 30 particles, which means if you move a class sort of through the class, and you move it through the class, it sort of has this edges where it could create like a completely different motions compared to the real one. So yeah, it's more of a simulated issue than this is an issue.
Do you have any thoughts on how to improve that going forwards? Because obviously you can't just, if you're trying to make a game, you can't just add more and more particles to get the correct sound.
Well, the easier solution is to just increase the particles, or just use a different one. Because most of the off-the-shelf simulator use the particle-based system. And it's really hard to, because we need to consider, because this is a real-time system, it's really hard to sort of balance between the speed and the qualities. But for now, all we can think is to sort of increase the quality, or we could just, instead of calculating the speed of each particle, we could sort of have a one average particle in total, and yeah, that could also help solving this issue.
all right, I have to stop it here
Thank you.
because I think we are a bit